The next talk will be Dynamical groomed jet radius in heavy-ion collision by Adam. Please go ahead.
Hi, thanks very much for being here. Today I'm going to talk about, so I'm a student from Bergen, the student of Conrad. And today I'm going to talk about this recent papers that we wrote with Abba and Paul about dynamical grooming. My talk going to have like two halves. In the first one, I will talk about mostly the vacuum baseline that we calculated first, and then in the next half, I will like see how it changes in medium. So just an introduction, this been mentioned many times during this week, that the emission, so the QCD matrix element has this soft and collinear divergence property, which basically gives that if you have a high energetic parton that's gonna emit several particles which are soft or collinear, and because of that, if you would like to stick to a perturbative description of QCD object, then you have to consider multiple emissions and jets. The Lund plane, it's a useful representation of the phase space of the individual emissions. So for example, if you have an emission with a given angle and a given energy, then you can plot it on this plane where here are the small angles, here are the wide angles, hard emissions, soft emissions. The same phase space can be defined to jets, and the standard procedure to do this is that you first find the jet, you recluster the jet with the Cambridge-Graham algorithm, which basically reorganize your branching tree in angular ordered, and then by following the hardest branch, you can just plot each of the individual splittings on the Lund plane. And what you're gonna see is that you know the angle gonna decrease in the subsequent splitting. The reason why the Lund plane is useful is that because the different regions of the phase space separates different physics on the Lund plane or inside the jet. So for example, when the emission becomes soft, then the coupling of the running coupling becomes very large. And of course, the perturbative description after a while has to break down. And that basically gives you a boundary on this Lund plane. So each of the very soft emissions are non-perturbative, and then you cannot describe them perturbatively. There are other effects, for example, underlying events like multi-parton interaction or wide angle emissions, so emissions which are starting out of the cone, but they're still entering in it. So these are also further complication in perturbation theory, but these emissions are well separated in given corners of the phase space. If one would like to be less sensitive to this complication, the simplest thing what one can do is to increase the energy of the initial parton or the jet, and in that case, this boundary here will just simply shift up, and then you have more phase space for perturbative calculation, and the non-perturbative or more complicated part of the phase space will be less dominant. Another way, of course, what I was talking about, this is like a vacuum picture, which is kind of well tested. But of course, the question if you embed this whole thing in a medium background, you have recoil, medium response, and so on, how will this picture change? And the main assumption is that, which was kind of tested in some limits a couple of years ago in this workshop, that basically this kind of heavy ion underlying properties are still well localized at wide angles and at small pt, and because of this, and also then we can assume that when you increase the jet pt, so you increase this line to going up, then this structure basically will stay. So then it's useful to assume, or it's reasonable to assume, that if I define a cut on the phase space, I can just simply get rid of this complication I mentioned before. And one of the simplest things that one can do is the soft drop grooming, which basically puts a hard cut on the phase space, and it says that I don't care splittings, which happens below of this cut. Of course, the soft drop grooming then will have parameters like which can change, the slope of this line, and of course the offset. And depending what I choose, I can be more or less sensitive, to this underlying event or like initial state radiation effects, or like wide angle radiation effects. The topic that I'm going to discuss today is another grooming, which is called the dynamical grooming, which is it's a more automatic, more like fluctuating grooming, which doesn't put any hard cut on the phase space, but instead try to select which one is the hardest, which one is the most dominant emission inside the jet. So for example, one can ask which one has the hardest KP, like this A = 1, and then you will be more sensitive to the things towards on the top of the Loon plane. So for example, this yellow point. You can also ask which one has the biggest mass. For example, if you want to tag heavy objects inside your jet, or you would like to tag short objects inside the medium, like which has the shortest formation time, then you will go rather to this red point in that direction of the phase space. So as I mentioned that at first we wanted to understand the analytic properties of this observable, of this dynamical grooming procedure. And here's just a very short introduction that how to imagine a calculation such. So the question what you will ask, that I have a jet, and inside the jet I tag one dynamical grooming object, which is the hardest inside the jet. So what I know that there is an emission on the Loon plane, which is the hardest, meaning that there is no any harder object inside the jet. So for example, in this red area, I know that there is no emissions inside my jet. Therefore, in the red area, I have to calculate the no emission probability because there's no emission there. And then I also multiply the probability that I have an emission at that exact point. As I said, this is a double differential probability. So for example, if I would like to calculate what is the angle of this emission, of this hardest emission, then what I have to take is this double differential probability distribution, and I just have to integrate out all the possible z's that this splitting had. And by that, I just moving this this point down, and I calculating more and more no emission phase spaces. If I would have the soft drop, then it would be a bit different, because in the soft drop you have, for example, a hard cut here. And because of that, you don't have to integrate down onto 0z, but you will have, like a minimum z, for example, where you cross this boundary. Of course, if you would like to acquire a high accuracy, then there's certain objects that you have to include your analytical calculation, like fancy splitting functions and fancy running coupling, and like other terms like non-global contribution, like emissions going out of the jet cone and then entering in again. So this is what we spent time on the first paper, and we came up with this quite high accuracy, which is next to double log. It's like a kind of similar thing to next to leading log accuracy. On this plot, what I would like to show you is that the dashed line is a double logarithmic approximation, like the very standard approximation we were discussing many times during this week. And the full line is this more precise, more accurate calculation we have. So what you can see with the green line is that the dashed line and the full lines are quite different. They differ, I don't know, in the 40% level at some point. And that's completely fine, right? Because one of the dashed line makes a lot of assumptions, and then you go for a more accurate description. What is the interesting is that if you, so this was calculated for 70 GeV, but if you calculate this for 1000 GeV jet, so you increase this phase space of the perturbative part, then basically the difference between the DLA approximation and the fancy resummation will shrink, because this higher order logarithms becomes less dominant compared to the leading approximation. And that's why, you know, jet people in the PP community, they always like just saying this mantra that higher PT jet is the better. That's basically. So we did this calculation to compare to some Alice data they had. We get a quite good agreement, but the Alice data was taken in 70 GeV. So we get a quite okay agreement with the data. This is PP, sorry, for different grooming parameters. But the thing is that there's a difference between the analytical resummation and then including non-perturbative corrections, and that at this limit, or this PT, this non-perturbative, what am I doing? Yeah, at this PT, the non-perturbative corrections are quite sizable, but still we get an agreement with the data. So just to recap, I introduced dynamical grooming, which is a kind of procedure to get rid of stuff that you don't want to describe with perturbative QCD. Based on that, we made this vacuum calculation as a baseline, and we show that we have a kind of understanding and agreement with the data they measure there. So the question, how will this change for heavy ions? So we simplify our problem a bit, and we say we stick to this double logarithmic approximation. And if you remember, I showed you that the double logarithmic approximation is not as good as long as the PT is not super high. So that's something what we have to live with. And then on the top of that, we also have medium-induced emissions, for which we use this simple BDMPS Z approximation, which we know that it's valid in a given corner of the phase space. The question is that what should we do with these two emissions? There are vacuum emissions, there are medium-induced emissions. What should we like? Should we sum up them? Where they, you know, what to do with them? And that's where the resolution comes to the picture. So to introduce the medium-induced or the medium-modified emission phase space, I kind of refer back to Paul's talk, who spent quite a time on this week. But basically, what we're doing, that there is this Lund plane, as I introduced. And for example, if one can what is that? So the emissions have a formation time, which basically means that how long does it take to this emission to be formed? Like how fuzzy this emission is, like when can I see that there are two objects from the emission? And then I can ask that when is this time scale comparable with the medium size? So basically, if the time scale of this formation is much longer than the medium size, then what I can see that the whole particle just went through the medium and then it split. So this is the blue region, which is basically we consider as an out of medium region. On the other side, in this triangle, there are emissions which are formed inside the medium. There is this other scale, is that when the formation time, when the separation of these two particles are somehow comparable with the medium scale, with the characteristic of the medium. And that's what will end up in this red line. So basically, all emissions inside this red region will split early in the medium, and then they have time enough to accumulate enough transverse momentum in the medium that the medium going to see them as separately when they leave the medium. There's also this veto region, the purple, that was Paul was discussing. I don't want to go into detail. And then what we also had to include is the energy loss and this bias, this whole bias effect, for which we use the quenching weight. So basically, what we said was that when you have an emission which is formed outside of the medium, then this whole object, like the whole splitting, was not resolved by the medium. The medium couldn't see that there were like there was an emission. Therefore, the total charge get quenched or start to lose energy. While inside the red region, the emissions were resolved, and therefore both of the legs are going to get energy loss. So by piecing together all of these ingredients in this toy model, we could calculate the dynamical groomed, the hardest theta G distribution. And what you can see here, like barely, is the blue line is the vacuum that I just showed in the first part of my talk, while the gray line is the medium modified that you can not see, but I will describe to you. So what you can see, there is a suppression at big angles, and there is a big enhancement at small angles. And basically, the reason of this is that wide angle emissions lose more energy because they are created in this part of the phase space, and you're going to observe less because of the bias effect, while small angle emissions lose less energy, you will see more of them. The reason why is, so probably you can't see, but the jump is this size. The reason why you see a huge jump there is because of the phase space of this thread. So there is a big difference between this theta C, this line here, because emissions on the left will lose a lot of energy, emissions on the right going to lose less energy. So we were quite interested that if you vary this dynamical grooming parameter, how will this jump change? Like, will it increase? Will it decrease? You know, which A is the best to measure this effect? The other question that one could ask is that I just presented you one of the phase space. Like, this is the phase space of in this factorized picture. There is a phase space in matter. There is a phase space in Joule. There is a phase space in Lido. You know, and those are not the same. So for them, the transition around this theta C or whatever scale they have going to be different. So that's again something that you can compare. So what we wanted to see is that how sensitive this theta C to different effects, or this jump, how sensitive is to that, especially to medium response, or especially varying, you know, energy loss models. So we use JetMed, we use Joule, we use hybrid, which basically all have different phase spaces. They all have different energy loss models. They have some kind of fluctuation of the geometry, and all of these things gonna, you know, vary the phase space. So what I'm showing here is the results with the JetMed, which uses a very similar picture that I presented in this toy model in previous. So the blue line is the vacuum, and the red and the gray line is basically the medium. And what you can see that around this theta C, or around the end of the resolved phase space, there is a big jump in the emissions, as I said, because of this bias effect. Small angles are less quenched than wide angles. So we did this analysis for each of these Monte Carlos, varying this A parameter, and we tried to find, you know, which one is the most suitable to find this jump, like how to characterize this jump. And we use this Kolmogorov-Smirnov distance, which is like this statistical tool to see the difference between two distributions. Well, that's an unfortunate. The Adobe Reader is not very pleasant, I have to say nowadays. So what we were interested is this medium response, like how the medium response going to change basically this business. You can't see it? Okay. Okay. Thank you for noticing. So okay, so what I have here is the calculation from the hybrid model with and without the medium response. So with the medium response, or without the medium response, we have the gray curve, big enhancement around this theta c scale, and then the gray curve goes here. If you turn on the medium response, you basically kill kind of some part of this enhancement, and then instead you have a big bump at large angles. So now I'm stopping back the way how I started my talk. So grooming is introduced to get rid of stuff that you don't necessarily want to discuss, or they will make your calculation messy. We introduced this dynamical grooming to get rid of the background. Hopefully we can get rid of medium subtraction. And now what I'm showing you, that the medium response is still there. That's a very sad thing. But our explanation of this is that the PT range that we studied here was the 70 GeV. So basically 70 GeV, if I recall this plot from Jewel, the 70 GeV line is basically very close to this medium response blob, you know, and that's why even though the grooming gets rid of some part of this, there is still something remain. So if you would like to reduce this effect, for example, you have to increase the PT of the jet, or, and this is what we did, we decreased the size of the jet from 0.4 to 0.2, because when you reduce the size of the jet, then basically from this line you cut it to the left. So we didn't change anything with the grooming, we didn't change anything with the samples, we just took smaller jets. And when you do this, and that's what you should look on the left, that basically with and without medium response, the gray and the red curves overlaps, and this problem went away. So for example, what we say now, these curves or this dynamical procedure and this dynamical grooming parameter that we had is the least sensitive to effects that we perturbatively can't really describe as well, like medium response, but it's very sensitive still to the phase space, which emissions are resolved and going to lose energy and which not. So by measuring this at a high precision, hopefully one can make difference between the different energy loss models. So like not the energy loss models itself, but like the emission phase space that the different models have. Yeah, I think I just summed up in the previous sentence, so I'm going to skip this slide. Yeah, thank you very much.
Any questions?
Hi, thanks. Very nice talk. Can you just go one slide 25, I think, sorry. With the blunt plane of the jewel. Yeah, so I didn't quite understood what you were saying. So this plot that you show is for hybrid, right? This one, yes.
Yeah, this one is the hybrid.
Okay.
This one is jewel.
Okay, but the scale for the medium response in jewel is much larger than would be for hybrid, right? So
could be, yes.
Okay, so why do you have such? I mean, I would imagine that if we looked at the Lund plane for hybrid, for instance, that blurred, if anything, for the hybrid would be below. So why are you so near some sort of medium response effects in this case? It shouldn't be there, right?
So what I tried to argue was a qualitative argument that similar to jewel in hybrid, there's also an area where you're sensitive to this medium response.
Okay.
And we are still sensitive to that with that wide angle.
Okay, thanks.
Yeah, thanks. That was a really nice talk. I have a question about what kind of cuts can be calculable. So if I'm thinking about this Lund plane diagram, and here you're showing theta G, for example. Do you have some guidance on? I mean, suppose experimentally we can carve out some region of this that we can measure, which probably will not be the whole thing due to completely experimental considerations. Is there input from the theory side of like if we have to make some slice in the double differential distribution what may or may not be calculable?
So for example, if one takes a normal, like just the soft drop, right, or the modified mass drop, like as it is here, you can see that you get rid of some part of the non-perturbative effects. But if you go at very small angles, then you end up having them. And then the same on the other side, if the angle is big enough, then this part can also be contaminated by wide angle radiation, which is hard to handle analytically.
I see. Okay, thanks.
Any other questions? You have a question? And to over. If not, then let's thank the speaker again.